In the last video, we started to talk about eigen concepts, where we basically saw about eigenvalues and eigenvectors. And we saw that we saw a general formula where if a matrix acts on a vector, it leads to the scaling of that vector by a factor lambda, which is known as the eigenvalue. All right. So, of course, we've done some computation of all these things in that video, but here we want to go into some more depth talking about computing eigenvalues and eigenvectors. So just like we saw in the previous video also, we saw things like we saw ideas like characteristic polynomial, eigenvalues, all right, eigenvectors too. So the first step is to get characteristic polynomial. You solve characteristic polynomial, you get eigenvalues. For each eigenvalue, you have a corresponding eigenvector. That's how this whole thing goes. So let's go uh, again, we have the introduction. So let A be a square matrix of order n by n. It has to be a square matrix. So a non-zero vector x, which is 0. In the other video, we said v. So anyone you choose does be consistent. So a non-zero vector x, which is non-zero, is called an eigenvector of A if ax is equal to lambda x. That is, if A acts on the eigenvector, the result you get is a scaling of the vector, right? So where lambda is a scalar, lambda is called an eigenvalue, and x is the corresponding eigenvector. The interpretation is that matrix A changes only the magnitude or direction of x, not its line, right? So it only changes the magnitude or direction of x. So it changes if lambda is positive, for instance. So if lambda is positive, whether it's positive or negative, so in magnitude, it changes the magnitude of x. Then if it is positive, the direction remains the same. If it is negative, the direction is changed. So, but the line remains fixed, right? That's why you have x on both sides. So so we go talk about characteristic polynomial now. So derivation, if you start with ax equals lambda x, by rearranging you have ax minus lambda x equals 0. So that means you have you can factor out x out now. So a minus lambda I x equals 0. So for a non-trivial solution for x equals 0, we require that the determinant of a minus lambda I must be 0. So this is called the characteristic equation, right? But if you want to look for the eigenvector, we cannot assume a trivial, okay, we cannot, yeah, in that case now we have to solve this now to get the trivial, to get the eigenvectors like we did in the previous video. So this is, but then the determinant of a minus lambda I equals 0 is called the characteristic equation. So without the equation part, determinant of a minus lambda I alone is called the characteristic polynomial. So just like what this topic tells us, but when you equate it to 0 and solve, when you equate it to 0, you get the characteristic equation, which when solved gives you the eigenvalues. So we have another definition here. So the characteristic polynomial of A is P of lambda, just like I said, P of lambda equals that or determinant of A minus lambda. For me, I like to use the absolute value kind of sign for determinants. So the properties now is that the solution of the degree of the characteristic polynomial is n, so it corresponds with the dimension of the square matrix. Then the roots are eigenvalues too. So the roots, so when you solve the characteristic polynomial, yeah, equate to 0, the roots you get are eigenvalues. So imagine this example right here. Let A be 2, 1, 1, 2. So A minus lambda I now will be, okay, well, I guess I just want to do this. I want to show, so I think we'll go step by step to look at this. So we have matrix 2, 1, 1, 2. Okay, so we have 2, 1, 1, 2. Let's call that A now. Okay, so to find the characteristic polynomial, that's the first step. To find the characteristic polynomial or equation, if you like. So you need to look for the determinant of A minus lambda I, you know. So 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 that equals 0 if you like to, right? Or yeah. So to find the characteristic equation, because I'm equating it to 0 already. So without the 0, it's polynomial. So we have A minus lambda I equals 0. So here we have that our A is 2, 1, 1, 2 minus lambda I, because it is a 2 by 2 matrix, we have a 2 by 2 unit matrix, 1, 0. So that's what represents 1. So in this case now, this 0 on the right hand side is also a 0 vector that makes all that work well. So you have 2, 1, 1, 2 minus lambda 0, 0 lambda, okay, equals 0, 0. So we then have 2 minus lambda, 1 minus 0, 1. 1 minus 0 is also 1. Then 2 minus lambda again, okay, equals 0, 0. And if you look for this determinant right here, so it means you have 2 minus lambda times 2 minus lambda, 2 minus lambda into 2 minus lambda, and that minus 1 times 1. So you have 1 right there. So, and all of that is equal to 0. Okay. So now you have, so you can expand all of that. So you have 2 times 2, 4. 2 times minus lambda, minus 2 lambda, minus lambda times 2, minus 2 lambda, minus lambda plus minus lambda is plus lambda squared, minus this one equals 0. So you can tidy all that up. So you have 4 squared minus 4 lambda, because minus 2 lambda minus 2 lambda is minus 4 lambda. Then 4 minus 1, that is now 3, equals 0. So this is what you call the characteristic equation. This is the characteristic equation, which when solved gives you the eigenvalues. So this is what you call the characteristic equation. Okay, so let's go back to the notes. So that's the characteristic equation, right? But if in terms of polynomial, so P of lambda, which is equal to lambda squared minus 4 lambda plus 3, is what you know as the characteristic polynomial. Characteristic polynomial. Okay, and this is like the first step for looking for eigenvalues and then later on eigenvectors. So let's talk about eigenvalues now. So the definition, eigenvalues are solutions of the determinant of ai minus lambda, the determinant of a minus lambda I equals 0. So the procedure is to form a minus lambda I, you compute the determinant from the by solving this. So you set this equal, form a minus lambda I, compute the determinant of a minus lambda I, then you set equal to 0, which is what you have here, and then you solve the polynomial. That's how you get your eigenvectors. So in essence, we are saying that to get eigenvalues now, so to find eigenvalues, okay, we solve characteristic equations. We solve equations, characteristic equations, which are formed by equating characteristic polynomials to 0. So this is what we want to solve now. So lambda squared minus 4 lambda plus 3 equals 0. So here we can, we can easily, it's quadratic, so we can factorize. So here we need two numbers which were multiplied. If you look, the coefficient of this is 1 and the constant is 3. So multiply the two, you get 3. Then the value you have here is minus 4. So you need two numbers. When you multiply, you get 3. When you add, you get minus 4. And in that case now, because this is negative here, so it means that you want so they have to be factors of 3, by the way. So it means you have 3 times 1, 3, right? But because you want this one to be negative, right? So it means since this one is positive, it means the signs of this one must be same. So if it is plus plus, you won't get minus 4. So you can do minus minus. So minus 1 minus 3 is minus 4. Minus 3 times. So you have minus 3 times minus 1, and you have minus 3 minus 1. So that actually works. So in that case, you have minus 3 and minus 1 for your factorization. So you have lambda squared minus 3 lambda minus lambda. So minus 3 minus lambda is minus 4 plus 3 equals 0. So we can then group. We have lambda squared minus 3 lambda minus lambda. Because minus is outside, this becomes minus inside, equals 0. So then you can factorize. So we have lambda into lambda minus 3 minus lambda minus 3 equals 0. So lambda minus 3 is common here. So we have lambda minus 3 into, lambda, if you cancel this now, you have lambda left minus 1 here equals 0. So because if you expand this now, you get that back. So it means you have lambda minus 3 equals 0 or lambda minus 1 equals 0. Okay? Because if the product of two factors is equal to 0, it means either one is 0 or both of them are 0. So lambda is equal to 3 here or lambda is equal to 1. So the eigenvalues of the original matrix. Don't forget the matrix 2, 1, 1, 2. That was what we started this. So the eigenvalues of 2 and 1, 2 are 3 and 1. Or let me even say 1 and 3. 1 and 3. Just to follow that order. So the eigenvalues are 1 and 3, like this. So as we can see here. So 3 and 1 or 1 and 3, as you like it. So that's that. But we can also have a 3 by 3 matrix, right? In the other video, we didn't do a 3 by 3 matrix. So this particular matrix, for instance, is very simple. Like I said, once you see, if you have if you have either if a diagonal matrix or an upper or a triangular matrix, so you can easily read off the eigenvalues from here. So from here, you can already see, because there's a 0 everywhere apart from the diagonal. So 1, 2, 3 are the eigenvalues. But of course, you have to go through the regular procedure of having so maybe I will do a 3 by 3 matrix at the end of the day. But this one now, we are just going to have the minus lambda along the principal, along the diagonal. So you have 1 minus lambda 0, 0, 0, 2 minus lambda 0, 0, 0, 3 minus lambda. So at the end of the day, you just have 1, 2, 3. So if you are doing an objective question, multiple choice question, and you are told to find the determinant of this matrix, don't even stress yourself. Just know that the values are 1, 2, 3. It's as good as, yeah, just know it's 1, 2, 3. Yeah. So, properties of eigenvalues now. So, first of all, maximum of n eigenvalues. So, if you have a 3 by 3 matrix, the maximum number of eigenvalues will be 3. If you have a 10 by 10 matrix, the maximum number of eigenvalues will be 10, right? So, the order of the or the dimension of the matrix will give you a corresponding number of eigenvalues. Then another thing is that the sum of eigenvalues is equal to trace of A. So when you add up the eigenvalues, that gives you the trace of the matrix, right? Then the product of the eigenvalues gives you the determinant of A. So you remember when we're talking about determinant, right? If you can put your matrix in echelon form and you multiply the elements on the principal diagonal, you have the determinant. So product of eigenvalues is determinant, while sum of eigenvalues is what you call the trace, like that. Then for triangular matrices, eigenvalues are diagonal entries. So for triangular matrices, eigenvalues are diagonal entries. So if you can make your matrix into echelon form, so you can just read off the numbers you have at the end of the day, and those will be your eigenvalues. So they'll be the diagonal entries. So this can give you some very sweet ways of getting your results without having to sweat it too much. Okay. So for eigenvectors now, by definition, for each eigenvalue lambda, like I said, a minus lambda I x is equal to 0. So the solution space is called the eigenspace now, right? So the procedure: compute a minus lambda I, then solve system, find non-zero solutions, write in vector form. All right. So for instance, this one that I've been working with before. So same matrix 2, 1, 1, 2. So the eigenvalues, we already know the eigenvalues from what we did before was 3 and 1, or 1 and 3 if you like. So for lambda equals 3 now. So you do a minus 3I and you get, so that'll be, okay, I think I'm going to do all that. But at the end of the day, for lambda equals 3, you have 1, 1 as your eigenvectors. Then for lambda equals 1, we have 1 minus 1. Okay. So let me quickly do that. So once I do that, you understand for 3 by 3 like that too. Okay, so in this case now we are still working on the same matrix, thankfully. So you already got the matrix 2 and 1, 2. We did all we had to do. We got the characteristic polynomial. We equate that to 0. We get the characteristic equation. We solve the equation. We get the eigenvalues. So the question now is, how do we find the eigenvectors? So we need to look for the eigenvectors. That's the next thing. So, but the eigenvectors now, an eigenvector corresponds to each eigenvalue. So that's the deal. So to find the eigenvectors, right? To find the eigenvectors. So you want to recall, you can just quickly recall that when you multiply a matrix, when a matrix operates on a vector, it scales the vector. So you have lambda v, right? So what that simply means is you can then go ahead and have AV minus lambda v equals 0. Then you can factorize the v. So you have, so if you factorize v now, so you have a minus lambda. Of course, because this is a matrix, this is a scalar, you have to multiply by the unit vector so that it will balance out. It can be both matrices. Then v can come out now equals 0. From here, you discover that the absolute value of, so if you have the determinant of a minus lambda I is equal to 0. This is what gives you the characteristic equation, like we said the other time. This gives the characteristic equation, which you can get your eigenvalues. On the other hand, if you have it just the way it is, you have a minus lambda I v equals 0. So this v now will give you the eigenvectors you're looking for. Okay? So eigenvectors corresponding to each eigenvalue lambda. Okay? So let's go. To find the eigenvector, for, okay, maybe we should remind ourselves, you recall again, all right, recall again, the eigenvectors or the eigenvalues of 2, 1, 1, 2, right, are 1, comma 3, okay? So we then go to find the eigenvector, corresponding to lambda 1, which is equal to 3. So this simply implies that lambda 1 is 1, sorry. You can use any order, it doesn't matter. Or and lambda 2 is 3. So let me take lambda 1 to be 1, okay? So to find the eigenvector corresponding to lambda 1 equals 1, don't forget we are looking for a minus lambda I. We are looking for v, this v that satisfies this, to be 0 now. So again, we now have, this is now a is 2, 1, 1, 2 minus lambda. So our lambda now is 1. So we have 1 into I, which is 1, 0, 0, 1, okay, multiplied by v. So this v now can then be v1, v2, and that is also equal to the 0 vector 0, 0, like this. So we are looking for this v1, v2 now. So what do? We try to tidy this up. So we have 2, 1, 1, 2 minus 1. 1 multiplies all this. So we have 1, 0, 0, 1, the way it is. All this now multiplied by v1, v2 equals 0, 0. So that means that we can then subtract 2 minus 1 is 2. 1 minus 0 is 1. 1 minus 0 is 1. 2 minus 1. Oh, so 2 minus 1 here is 1. Sorry. 2 minus 1, 1. 1 minus 0, 1. 1 minus 0, 1. 2 minus 1 is 1 again. Into v1, v2 equals 0, 0. So we can expand this now. Because we want to multiply, this is 2 rows, so it means we have to write this twice. We have to write the column twice. So that means we have v1, v2, v1, v2. So you can put this over it. So you have 1, 1, and then 1, 1 again. And that is equal to 0, 0. So that this is now v1 plus v2 equals 0. Anyhow you like it. So, v1 plus v2 equals 0. Again, v1 plus v2 equals 0. So it's the same. So it's the same. So you can pick any one. So v1 plus v2 equals 0 simply means that v2 is equal to minus v1. Okay, v2 is minus v1, and so that means you have infinitely many solutions. So you can just choose. So if you say let v1 be equal to 1, automatically v2 will be equal to minus 1. So v1, v2 will just be 1 minus 1. Okay, so we have, you can then say you have, for eigenvalue 1, the eigenvector is 1 minus 1 easily. Okay, so that's for lambda equals 1, eigenvalue lambda equals 1 now. So we can go for the next one. For lambda equals 3, right? For eigenvalue lambda equals 3, again we have a minus lambda I multiplied by v equals 0. So we are looking for this v again. So we have so we still have 2 1 1 2 minus 3 now. Lambda is now 3 into 1 0 0 1 multiplied by v1 v2, and that is equal to 0 0. So we have so we tidied things up. So we have 2 1 1 2 minus 2 1 1 2 minus 3 0 0 3, like that, multiplied by v1 v2, and that is equal to 0 0. So that this is now 2 minus 3 minus 1, 1 minus 0 1, 1 minus 0 1, 2 minus 3 minus 1, and that is into v2 equals 0 0. Again, we have two rows here, so that means we are going to write each column twice. So you have v1 v2 v1 v2. We have only one column, by the way, so this is not minus 1 1, then 1 minus 1. So all that is equal to 0 0. So that means that if you multiply out, you have v1 minus that's minus v1 plus v2 equals 0. On the other hand, we also have v1 minus v2 equals 0. Anyhow you like it, the two equations are the same, right? The two equations are basically the same. So they are technically the same, because this one is also, if you multiply 3 by minus, you have minus v1 plus v2 equals 0. So that simply tells us that v1 is equal to v2. Anyhow you look at it, v1 is equal to v2. So if v1 is equal to v2, what does that mean? If v1 is equal to 1, v2 is also equal to 1. So we have v1, v2 to be equal to 1, 1. And that implies that when the lambda is 3, then when the eigenvalue is 3, the eigenvector is 1, 1, basically. So that's the idea about eigenvalues and eigenvectors, like that. So that's exactly the deal here. So for lambda equals 3, you see we get 1, 1. And then for lambda equals 1, we get 1 minus 1. We got 1 minus 1 before for lambda equals 1. Okay, so for lambda equals 1, we got 1 minus 1, as you can see. That's for lambda equals 1. Then for lambda equals 3, we have 1, 1. That's exactly the deal right there. Okay. So, I mean, don't worry yourself about this case. At the end of the day, it's what you have in bracket that really matters. So for 3 by 3 matrix, it's the same process, right? So you just have 4 1 0 0 2 0 0 0 2, and then, okay, maybe I should just try to work that out as much as I can. So 4 1 0 0 2 0 0 0 2. Okay, 4 1 0. So let's say you have B to be 4 1 0 0 2 0 0 0 2. And want to find eigenvalues and eigenvectors. Okay. I may not go into all the detail. I'll just do the sketches. So first of all, to find to find to find characteristic equation, to find the characteristic equation. Okay, what do? We know this is the determinant of b minus lambda I equals 0. So that means we have the determinant of b itself is 410, 410, 020, 002. I hope that is what the matrix is. I want to be sure of that. 410, 020, 002. Okay, that makes sense. So that we then have minus lambda I. We don't know what lambda is. This is a 3 by 3 matrix, so we have 1 0 0 0 1 0 0 0 1. So this is a 3 by 3 matrix now, so you have to do it like that. So, and then this is 0 0 0. So in this case now, then we have the determinant of 4 1 0 0 2 0 0 0 2 minus lambda 0 0 0 lambda 0 0 0 lambda. Okay, and that is equal to 0 0 0. So from there now, then you have the determinant of 4 minus, so subtract, you have 4 minus lambda, that's corresponding terms, 4 minus lambda, 1 minus 0 is 1, 0 minus 0 is 0, 0 minus 0 is 0, 2 minus lambda, right here, 2 minus lambda And then 0 minus 0 is 0. Then 0 minus 0, 0. 0 minus 0, 0. 2 minus lambda. That's 2 minus lambda right here. And that is equal to 0, 0, 0. Okay, well, I mean, everything has to be 0 now because we're talking about determinants. I think it's proper. Because we're taking determinants, it's no longer a matrix. So it's just 0 like this. So take the determinant. What do we do? For a 3 by 3 matrix, you already know what we do. This is plus minus plus. Or let me change the marker to drive home the idea. So this is plus minus plus. So usually we say plus 4 minus lambda into cross this and cross this. So cross this and cross this, we have that's 2 minus lambda 0, 0, 2 minus lambda. So we have that. Then next, we have minus 1 into cross and cross. So that means cross this and cross this. Okay. So that's all I see there is 0, 0, 0, 0, 2 minus lambda. And lastly, you have of course, this is equal to 0 now. This is equal to 0. Okay. So lastly, you have plus 0 into cross this and this. So you have 0, 2 minus lambda, 0. We don't have to worry about this actually because it's already 0, right? So but I just like to do all these things. 0, 2 minus lambda, then 0, 0. And everything is equal to 0 now. So of course, this goes to 0 normally. So here you have 4 minus lambda into, take the determinant. So you then have 2 minus lambda, 2 minus lambda into 2 minus lambda minus 0 times 0, 0. Then minus 1 into 0 minus lambda, 0, 0 times 0, 0. So plus 0 into everything. That's still 0 right there. So all of that now is equal to 0. So all these are gone. All right. So we have 4 minus lambda into 2 minus lambda. Okay. Into 2 minus lambda into 2 minus lambda because this is 0 also. Then everything is just 0. So from all we have here, we see that lambda is equal to 2, lambda is equal to 2, and lambda is equal to 4. So the eigenvalues are 2, 2, 4. So you see there's multiplicity of 2 here because I mean this is already a triangular matrix, so you can note the eigenvalues are already 4, 2, 2 from what I said. So if you didn't have to work all this out, you can just read that off and move on, move on like that. So the eigenvalues are just 4 and 2 because 4 appears once and 2 appears twice. So you can then begin the process of looking for eigenvectors. So let me do eigenvector. Since we have to, it makes the whole thing easy. So let's go. So at the end of the day, we have 1 minus 2, 0 and 0, 0, 1. So let me just go ahead and still continue with that because this is the first time I'm actually getting down to do it for a 4 by 4 matrix, for a 3 by 3 matrix. So to find to find uh eigenvectors for lambda equals 2. Okay, the matrix is 4, 1, 0, 0, 2, 0, right? So you know we have a minus lambda I into multiplied by v, right, is equal to 0. So that means we have 4, 1, 0, 0, 2, 0, 0, 0, 2 minus lambda is 2 is the focus here. So lambda, so we have a unit matrix corresponding to that. Okay. All this now multiplied by the vector. So now we have 3, v1, v2, v3, okay, equals 0 vector 2, column vector rather, that's 0, 0, 0. Then that means we have 4, 1, 0, 0, 2, 0, 0, 0, 2 minus 2, 0, 0, 0, 2, 0, 0, 0, 2, okay, into v1, v2, v3, and that is equal to 0, 0, 0, like this. So we then have 4 minus 2, 2, 1 minus 0, 1, 0 minus 0, 0, 0, 2 minus 2 is also 0. Yeah, so 0 minus 0, 0. What else? 0 minus 0 again, 0, 0 minus 0, 0. 2 minus 2 again is also 0, interestingly. So all this now is multiplied by V1, V2, and V3, and this is equal to 0, 0, 0. All right, interestingly, normally if everything was to be fine, would have had 1, 2, 3 rows, so we have to write this 3 times. So I'll still go ahead and do that V1, V2, V3, in case you have a full-blown case like that. V1, V2, V3, and then we have V1, V2, V3. That's a lot of stress, but it's okay. Just for the sake of clarity. So this is 210, then all this is 000, and this is 000. Thankfully, we have plenty zero, so everything just goes to 0, 0 like this. So now the only issue we have is for the first case, we have 2V1 plus V2 is equal to 0. Okay, all these other ones just are wasted. So we only have things connecting these two. So first of all, you can see V3 is not here at all. So it means V3 can take any value. That's what that simply tells us. But for this V2 we have, so we see here that V2 is equal to V2 is minus 2V1, right? V2 is minus 2V1. So if V1 is equal to 1, all right, that means that V2 is automatically minus 2. So we can also take uh, so we can just say let V3, which we don't know, be also, we can make it 0 or 1 or anything we want it to be, since it doesn't have throw up any value directly. So we just take it, this is for lambda equals 2. That's the first thing I did, right? Lambda equals 2. So so in this case, I just have like okay, well, trying to think of what to do. Yeah. Okay. So let's do this kind of thing I did the other time with when I was looking for is it basis and dimensions or something like that? Yeah. So maybe we can just work with what we have here. So here now, if we let if we let if we let okay, I think I want to borrow a leaf from what we did here so that it won't be too far from it. So you can see there's no z here, right? So we say z is t and x is y. So z is t and z is t and x is s. Okay. Um okay. So basically this is what we have now. So we can just say let v3 be equal to t, and then um okay, to make this is the last one we have, right? That's the same thing as when we say that V2 is equal to minus V1, right? So we know that much. So we can just say let V3 be T, and then and V3 is T and V2 is equal to S, right? V2 is equal to S. I want to correspond with this. Okay. Yeah. I mean, you can do it anyway, but I just want to follow that. So V3 is T and V1 is actually S. Okay. And you know how we do this normally in other cases. So here now we have V1 is S, V2 is minus V1, which is minus V2 is minus V1, which is equal to S. So in short, V2 is S, and then V3 is equal to T. So based on this now, we can form the collection. So we have V1, comma V2, comma V3, is equal to, so in terms of S and T now, so if you take S, so V1, right? V1 has the coefficient is 1. V2 also has S, that's minus 1. V3 doesn't have S, that's 0. Then we go for T. V1 doesn't have T, V2 doesn't have T, V3 has this. So that's why at the end of the day, we have 1 minus 1. Oh, what did I say here? Something is wrong. V2 is minus 2V1, sorry. V2 is minus 2v1. Sorry. So this means v2 is 2s, right? So okay, v1 is s, right? V1 is s. Yeah, v1 is s. So that means that with v1 being s, okay, v2, okay, v1 is s, right? So it means v2 is minus 2s. Yeah, v2 is minus 2s. So that means that for v2 we have minus 2 right here, minus 2 here. Yeah, I think that works. Then coming here now for t, we have 0, 0, 1. So 1 minus 2, 0, then 0, 0, 1. 1 minus 2, 0, 0, 0, 1. Exactly. So that's the deal. So we have this now. So the eigenvectors corresponding corresponding to lambda equals 2 are 1 minus 2, 0, and then 0, 0, 1. So if you want to write it the way I've been writing it, so this implies that we have 2, comma 1 minus 2, 0, and then 0, 0, 1. But that is just for lambda equals 2, right? So we still have lambda equals 4. Thankfully, if they were distinct, we'll have to look for eigenvectors for 3 different eigenvalues. Thankfully, after this lambda equals 2, we can then just do lambda equals 4 and we are done because 4 is repeated, 2 is repeated twice, I think. So to find to find eigenvectors, okay, corresponding to lambda equals 4. We did lambda equals 2 right now. So corresponding to lambda equals 4, what do we do? Again, the formula, this is lambda minus, I said b, right? B minus lambda I multiplied by v equals 0. So again, what is b? B is 4, 1, 0, 0, 2, 0, 0, 0, 2 minus 4 into 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, all this now multiplied by v1, v2, v3. Okay, and that is equal to 0, 0, 0, like this. So we tidy this up. We have 4, 1, 0, 0, 2, 0, 0, 0, 2, like this, minus 4, 0, 0, 0, 4, 0, 0, 0, 4, like that, into v1, v2, v3 equals 0, 0, 0. Okay, so we tidy that up further. 4 minus 4 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 0 minus 0, 0. 2 minus 4 is minus 2. 0 minus 0, 0. 0 minus 0, 0. 0 minus 0, 0. 2 minus 4 minus 2. Okay, and that is into v1, v2, v3 equals 0, 0, 0. So we can multiply things out now. So every 3 rows, so that means we write this column thrice. So v1, v2, v3, v1, v2, v3, then v1, v1, v2, v3. So we just put this over is this 0, 1, 0, this first row, 0, 1, 0, second row, 0 minus 2, 0, third row, 0, 0 minus 2. Okay, all of this now is equal to 0, 0, 0. So if you equate everything, so v1 is gone. So we just have v2 is equal to 0. Okay, v2 is 0. Next, so v2, right? Because v1 is 0. So v2 is 0. Then the last one, yeah, that thing is 0, 1, 0, right? So v2 is 0, right? The next one also, we have minus 2v2 equals 0. So it's consistent. V2 is still 0. Nothing special. Then lastly, we have minus 2v3. Minus 2v3 is also minus 2v3, right, is also 0. That implies v3 is also equal to 0. So in this case now, conclusively, v1 doesn't even feature at all. Conclusively, we have v2 to be 0, v3 is 0. So v1 we don't know, v1 we don't know. So we can just assume any value for it. So let v1 be equal to 1. So pick the smallest value, not 0 anymore. So we have we then have the we have the eigenvector to be v1, v2, v3, which is equal to 1, 0, 0, because we have v2 and v3 conclusively to be 0. So this simply implies that for eigenvalue of 4, the eigenvector is 1, 0, 0. Okay? So that's what we have in that case. So that's how that goes like that. So for 4, as you can see, we have 1, 0, 0 like that. Okay, so that's how to find eigenvalues and eigenvectors. So that should help a lot to clarify that idea. So let's talk about multiplicity now. So in the case up there, we have multiplicity, right? Because you have 4, 2, 2. So 2 appears twice and 4 appears once. So 2 appears, 2 is the eigenvalue with a multiplicity of 2 because it appears twice. So we talk about algebraic multiplicity. So number of times an eigenvalue appears as a root. That's what is called algebraic multiplicity. So like the other case where we had 2 minus 4, I mean 2 minus lambda squared, that's multiplicity. As you can see, when we are looking for the when we're looking for the eigenvalue up here, so you see this here, it tells us we have 4 minus lambda into 2 minus lambda squared equals 0. So this shows us multiplicity 2. Okay, multiplicity 2. So we have that eigenvalue with multiplicity 2 like that. So then in that case now, we say the algebraic multiplicity is equal to 2. Then we have geometric multiplicity. Geometric multiplicity talks about the dimension of eigenspace. In the next, is it the next video? Maybe in video 34, this is video 32, I'll be talking about eigenspace. So you can watch out for that. So when you talk about dimension of eigenspace, it is always that one the geometric multiplicity is always between 1 or 1 and the arithmetic multiplicity. So 1 is always less than or equal to the geometric multiplicity, which is always less than or equal to the arithmetic multiplicity. So for the complete method for looking for eigenvalues and eigenvectors now can be said to be like this. Step 1, you find eigenvalues by solving the characteristic polynomial that a minus lambda I equals 0. Solve the polynomial. Step 2, for each eigenvalue, form a minus lambda I, solve system and find basis. So basis are all these matrices I've been looking for. Those are, it's just like finding basis as usual. So all these matrices we found, so especially when you come to this something like this and you do all these things and these are now like your basis. So that's what we end up having here. So for 4 also, at the end of the day, conclusively, you have v2 and v3 to be 0. So v1 is missing. So it means v1 can take any value. So that's why we have this here. So like it's like you forming basis like we did the other in other cases. Then apart from that, you write the eigenvectors, which you can express in parametric form. Okay, you can express them in parametric form like we did. Then these are the common mistakes you should pay attention to. Forgetting identity matrix is usually a mistake. Then wrong determinants, can make you miss it. Then using zero, I mean, determinants can be confusing, especially when the matrix becomes bigger. Then don't forget identity matrix, of course. Using zero vector. If you forget to use zero vector on the right-hand side, you can have a problem. Arithmetic errors, like, because of the many numbers, you can mix things up. So watch out for that. Then missing free variables can also be a problem right there. So we have some practice problems here. Well, I think from what I've done already, I think I've done so much justice to this so that any question you have, you'll be able to handle them yourself. So find the eigenvalues and eigenvectors of each matrix. You already know the procedure. So this is 1 to 4 now. Let me do 5 to 8 again. So for 5 to 8, you have all this. So eigenvalues and eigenvectors, you already know what to do. So same for this. So yeah, it's been such a sweet time working with this. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. Um, if you have subscribed to this channel already, I must thank you very much for doing that. If you haven't, why not go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of the channel by clicking on join. That gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.